Okay, we can start from the previous model. We can modify directly this model. If you select everything, you can delete it by press cons. I'm going to check the material, but we can use the same material. Again, the important thing is only the elastic modulus. I take it the same, 210, and the Poisson ratio, because as I told you, everything is elastic linear. So I am not interested on the value of the yielding and the ultimate stresses. Define the new cross section by import the IPE again. As the last time, we can import by selecting euro because it's an European profile. We can look for the IPE 400. I don't want to consider the shear deformation again. You can check the properties and look if are the same of the last time. Okay, now we have the material, we have the cross section, we can define the grid. I'm going to modify it's the same, I can modify the X direction and create this rectangular 1000 by 4000. Okay. We can draw a beam element. Pay attention here to select the IPE 400 and not the C section. From 0 to the last point. If you want to check your cross section, you can extrude. And you can see that is a double T cross section. For the buckling analysis, it's better to have a discretization of your beam because the buckling results are really influenced by the mesh. It's not like the previous cases on which we can find the exact value by using only one or two elements. Here the influence of mesh is quite important. So again, we can divide the frame by edit lines, divide frames. 10 elements are enough. And then, as as I showed you previously, we can assign we have to assign the external restraint that again is a fixed joint. I put a fixed joint here on the 0 point of my beam. And we can assign the axial load, joint loads, forces. Pay attention that this time is an axial load, so is in the x direction, 1 kilonewton. Okay. I use the same load pattern that I have created before, that is force. Selecting this point, you can apply an axial load. So, fixed point and axial load. Now, the important thing is to perform the buckling analysis. So, when you go in define and in the load cases, new load cases, of course, buckling, you can select from this menu buckling. This is a quite common way to perform a buckling analysis in all the software, also in Midas and I don't know, Abacus. You have buckling, linear perturbation or buckling, that you can see always this kind of option. We are saying to our software to perform the eigenvalue and eigenvector problem by considering elastic stiffness and geometrical stiffness matrix. And like in the static case, we have to define the type of load pattern and add. Here we have one more option, that is the number of buckling modes, because as I told you, you have a lot of buckling modes, a lot of buckling values. If you think about a real frame, you can have 200 or 300 buckling mode, but you are interested in the first, maybe only in the first one. So you can reduce the time of the analysis and select like 6 or 10 buckling modes. This is a more complex problem if you are performing a shell buckling analysis, an analysis on shell element, because if I'm performing a buckling analysis on these shell elements, if I am interested only on the global mode, I will have for sure a lot of local modes, like these flanges that go in local buckling, or something like wave on these flanges, some wave on this plate. And you have to go ahead, you have to looking for your global mode. Maybe it will be the number 20 of your, you will have a lot of buckling mode, and the global one will be the 20 or the 30 on the, depends on your beam. But for our case, 10 are, we are interested only on the first one or on the third or on the second. This is the convergence because this kind of analysis is an iterative analysis. You can have a lot of methods to resolve this problem, that you have the Lankos method, you have the Jacobi, You can have subspace iteration. These are numerical methods to resolve the eigenvalue eigenvector problem. In SAP, there is not the possibility to change the method. But sometimes by changing the method, for example, Lancos can give you no value, can fail, but by using Jacobi, maybe you can find the value of the eigenvalue. If you are interested in the pure mathematical detail, we can talk together. I can give you, but now is not it's not really important now. And the scale factor is 1. Okay, we just run the analysis like did previously. I have also the linear static, of course. We can run or do not run, is equal, is not important. Okay, this is the first buckling mode. We can animate. You can see that is a pure flexular mode in the lower inertia plane. And the value is exactly the one that I calculated here. Because, as I told you before, the final value of the buckling is the applied load, that is 1, multiplied by this factor, 426. I apply the 1 kilonewton, so the final value is 426 kilonewton. Okay, SAP for this case it works. Because, as you can see, is a flexular and is the minimum one, is the first one. So everything is okay. I can look for other modes. As you can see, the second mode is 4000. So I skipped this mode. I didn't see this torsional mode. I pass directly from the flexural one to the second order flexural. It is this kind of shape, S shape. We can looking for this kind of flexural mode in the other plane. Maybe it's the third one. Okay, you can see that the third one is exactly this one. So I expected that this mode is a flexural mode in the other direction, not in the lower inertia direction, but in the higher inertia direction, so in this plane. And if you go ahead with the other modes, you will see higher modes that are S mode and so on. Of course, if I put a multiplier 10 times, I will obtain 10 times lower buckling factor. So now I have 426.8. If I put here, in the load cases, a factor of 10, since everything is linear, I expected to obtain 42.68. And of course, I obtained 42.68 with the same shape. And of course, all the modes are scaled with the same factor. Now, if I put a bending moment, for example, about y-axis of 5 kilonewton meter, if you select replace, SAP will replace the previous case, so the previous load. If you just add the bending moment, you don't have to put here the forces. You have to put only the bending moment and press add. So now you can see we have axial forces and the bending moment. If you want to look directly what you have in the node, you can select the node and do a right click on the node. You will see load. You can see also the location, the coordinate, and the loads. This is unuseful information because if you have a lot of nodes, you can select one node and be sure that you have applied the right loads. Okay, I'm going to put 1. As I told you, SAP consider only the actual value of the loads on our beam, so I expected to obtain the same results, 4 to 6. And you can see that the bending moment have no influence on my buckling results. Last thing on this IPA, if I put only the bending moment, so again replace, I'm going to select this node and putting only the bending moment, If I perform the buckling analysis, you can see that nothing happened. It's not able to perform the analysis because in this case I don't have any actual load on my beam. So SAP is not able to create the geometrical stiffness matrix, so it cannot perform the buckling analysis. Did you find the value of the buckling multiplier? I can show you now what happened with the C cross-section. I'm going to use the same C cross-section that I showed you before. I think you already have on your SAP implemented. We can change the length in 1 meter. For this cross section, the flexural minimum one is for a C cross section, we have that the buckling, the flexural torsional buckling, is 3 times lower than the flexural one. But if you perform an analysis with SAP, you will obtain always this value. To obtain this value, we need a 7-DOF beam. We can try to use SAP. If you select everything, you can delete by using Kant. I'm going to create a new grid by modifying the length. I can draw directly the C section because I have in my menu is the one that I have defined before. I can show you again the properties of the C section. I'm going to split into 10 elements. And to create the cantilever beam with the 1 meter of length and axial load applied. You can check the visual by using extrude. I did it quickly because it's the same that I just changed the length and the cross section. I don't have to define again the load cases because it's the same. It's the buckling. You can see that the behavior, the force buckling multiplier of our C cross section is a pure flexural one, but is not correct because from the theory I have a flexural torsional buckling that is 3 times lower. I can use conceal to calculate the right value. This was the C-section that I have defined previously. I'm going to modify the length 1 meter and to put the load. This time is an actual load. You can see also in Conceal we have buckling analysis. You can select directly buckling analysis. Here there is the cutoff. In Conceal you cannot select the number of modes, but there is a cutoff. That means from these values above, and you can cut the results from these values. So I'm interested in one values of more or less 56, 100. I can put here like 1000, so I'm sure to have a lot of buckling modes. Okay, you can see that the first buckling is not a flexural pure buckling, but is a flexural torsional. Because still you have here the menu that is buckling results. The first one is this flexural torsional buckling. And the value, you can see the first one is 5.7. It's quite different again because from the theory I have the differences in the torsional constant. So in constant is quite greater, so the buckling is a little greater. You can see that the second mode is exactly the one that SAP gives me. That is a pure flexural mode. And in Conceal you can also consider the influence of the bending moment. I put if I put a bending moment of 100 kilonewton meter on the top, together with the axial load, you can see that the buckling is quite, the beam is unstable because the buckling is 0. And also the modes change. I'm going to create a new SAP file. Again, the grid is not important now. Okay, first of all, I'm going to define the grid. My frame is 3 base and 2 floor. This is 4 meter. This is 4 meter. And the base are 5. So, in the x direction, I put 5 meter. You can write just once time and then add. If you have a new version of SAP. If you have an old version, it's not possible. And in the zeta, 4 meter and 8 meter. The plan of Blackboard is x and zeta. Okay. If you go on x zeta plan, you can see this kind of grid. Now I can show you a new option that is set analysis option. You can see that it's possible to avoid displacement in the other direction. We can choose to work on the 3D space, or like I want to do in this case, in x zeta plan. This is important because I'm going to design only a planar frame. So I don't want the buckling in this direction, out of plane buckling. So you can select here x zeta. You can see that available degree of freedom, some are selected and others are unselected. For example, in Consteel, this option is not possible. So if you want to study only in plane behavior, you have to put a restraint in the beam and in the column for the out-of-plane displacement. Okay, now we have to define the materials. I'm going to take the same elastic material because buckling is elastic analysis. Again, pay attention on the Young modulus and on the Poisson. And then we can import the cross section, frame sections, import new cross section, double T, European one. So I need HEB 220. All the columns are made with this cross section. And all the beams are made with the IPE 320 and 30. So we need to import two different cross sections, of course. On the list you can find the first one, and the second one. Again, pay attention to choose the right material, and if you want to look on the properties by comparing with the theoretical one, in order to be sure that the properties are right, are correct. Now we can leave also the shear deformation and everything. Okay, we have the material, we have the cross section. We can draw the beam. For this frame, everything is made with the beam elements. So pay attention to select the right element. So starting with the columns. I'm going to use always the same orientation. So starting from the bottom and going to the top. And the same thing for the beams, IPE beams, from the left to the right, always. So I want to have the strong axis on the plane. So this must be the orientation of the beam and of the column. I can check if the orientation is right with the extrude vision. Okay, everything seems good. I'm going to divide the elements into sub-elements to have a more refined mesh. Edit lines, divide frames. For example, 5 different elements for each element. So the boundary condition, first of all, with base joint, I'm going to put fixed condition on all of the base joints. So in this way, we have created a perfect rigid frame with the fixed base and continuous beam to column element. So everything is rigid. The connections are perfectly rigid. So we can transfer the bending moment. Again, this is an external restraints, joint restraints. Everything is fixed. You can fix everything, or you can fix just the displacement and the rotation on the plane. Because as you know, we don't have anything out of the plane. And now the last thing is the load. I'm going to define load patterns. Always live load because now I don't want to consider the self-weight. We can create 2 different loads that are vertical and horizontal. Vertical forces and horizontal forces. Load condition is distributed load on the beam and horizontal load. The distributed load is 100 Newton on millimeter, and the horizontal forces are 20 kilonewton. This is our F. We can define the distributed load by using a trick to select quickly all the. We can use two different tricks to select the beams. We can use select by properties. So this is a really important command, because if you have a quite complex structures, you can select, for example, all the beam with the same cross section. If you choose IP, you can see that all the beams, I have selected all the beams. Another trick is to select by using parallel beams, parallel lines. So if I click on one horizontal element, SAP automatically will select all the horizontal elements. And then you can assign, once you selected, you can assign the distributed load. Distributed load is not in the joint loads, of course, but in the frame loads. You can see in the frame loads we have a lot of loads like the deformation, strain, temperature, distributed, and so on. Maybe also fire load. There is something about fire. Pay attention to choose the right pattern that is vertical, global. Direction, I don't want to use gravity because gravity can be different. So I'm going to use zeta and uniform load. With this command, you can create trapezoidal load and so many different loads. I'm going to put 100 with the minus, of course. In my version of SAP, I cannot see the load by using the extrude version, visual, but only with the frame visual. These are the distributed loads on my frame. Then I'm going to put horizontal forces. Horizontal forces are joint loads. Horizontal in the x direction. I have 20 kilonewton. Okay, now everything is defined. We can create the load cases. We can create the linear load case by consider both the horizontal and the vertical. And we can create the buckling load case. First of all, I want to show you what happened with only the vertical loads. Then we can see the buckling with both vertical and horizontal. Okay, now everything is defined. We can push play button or we can push F5. To see internal bending moment and axial forces and so on, you can push F8. There is another command that is more useful. You can select the element on which you are interested by push Control T. You can generate the tables. I don't remember the command from the menu. I can look, display tables maybe, yeah. Display tables, show tables. And SAP will show you the information about the selected element. For example, if we are interested on the internal forces, you can select element output, you can select internal forces. Here you can see that you can select also the load cases. So for example, we can see the internal forces for the linear static analysis. These are the tables for the internal forces on the elements that I have selected. You can see that we have axial, shear, torsion, bending moment, and so on. This is useful because you can export everything to Excel. I cannot do it because it's an evaluation version, but you can export by using export to Excel. You can open SAP will open a new Excel file, so you can work on your data without checking frame by frame manually. Okay, now we can see the buckling. You can see that this is the first buckling, is a global buckling. And this is a classical sway buckling. This is classical buckling for the unbraced frame. We can save the value. $10.5. So if we want to know the buckling of this column, this is column 5, 10.5 multiplied by the value of the actual values, of course, related not to buckling analysis, but to load cases. That is 1000 more or less kilonewton. the buckling is more or less this one for the column 5. I want to show you what's happened if we change the internal stiffness of the beam to column joint. If you remember last time, for assign a different stiffness of the joints, we can use the releases. Now it's really important to check the local axis. To see what is the initial and the end for our beam. I can select all the initial beam of my IPA. And if you go in Assign Frame Releases, you can choose an initial stiffness for these elements. So I'm going to create on all of these beams a semi-rigid connection. Now it's perfectly rigid. By using releases, I'm going to use this kind of graph. Moment, rotation, linear. I'm going to use always the initial stiffness. Of course, start, because only the start element I have selected. If I use end, I will put releases on the end of the beam. So I'm interested only on the connection between column and beam. And I'm going to put 1.2 for the power of 6. You can write directly y.2 E6. That is a semi-rigid connection. If I put 0, I insert a hinge connection. From 0 to the stiffness of the beam, there is the semi-rigid region. It's not the stiffness of the beam, it's like 25, the stiffness of the beam. If you refer to the Eurocode, you have this limit. This is 0.5, the stiffness of the beam. Lower these values, you have the hinge. So here you have the hinge. And on 25, stiffness of the beam, you have from this value, you have the rigid connection. In this part, you have semi-rigid connection. You can see from the SAP that you have released some part of the beam. You can do the same thing with the end. You can see that I have created some releases, partial fixity. And what do you expect now? The frame is more deformable, so the displacement of your frame will increase because the rigidity of your frame is lower. And the buckling, in your opinion, will increase or decrease? The buckling will decrease because more flexible is the frame and more lower is the buckling. Buckling associated with the flexible frame is lower than the buckling associated with the rigid frame. You can think also to the cantilever. This buckling is lower than this buckling. If I perform again analysis without changing anything, you can see that the internal stresses are more or less the same. Something changed because the deformation is different and the axial force is quite different, but more or less are the same, of course. But the buckling, you can see that is really, really low because it's 1.45. So that means we are in the ingest zone, zone. If you try to calculate this value, for your beam, you will see that the hour stiffness that I use at 1.2 for the power 6 multiplied by 10 for the power 6 Newton millimeter rad is more or less something like 0.5 this value or more or less similar. So we are in the ingest zone, and for this reason we have this really low value of the buckling. Of course, if you increase the stiffness, you will increase the buckling until the other limit, the upper limit, that is 10.5, associated with the continuous frame. Okay, we can stop the analysis for today.